All right. You guys want to start with questions? I think at this point we've assigned up through 24. Does anybody have any homework questions? Grace? Yeah, sure. So 24 says, find all vertical and horizontal asymptotes for the function. So I'll start by just firing up my graphing calculator. I'm going to type this in. Hey, look at that. It's already in there. I'll go ahead and graph and take a look. When I look at this, I see three asymptotes. I see a vertical asymptote. What's that look like? 1, 2, -3. Another vertical asymptote at 1, 2, +3. And then a horizontal asymptote at y = 0, aka the x-axis. Okay, so let's write that down. And now let's confirm these. I'm going to do that with a table. So I'm going to start by picking some values that are less than -3. They get progressively closer and closer to -3. So I'll do -3.1, -3.01, and -3.001. And I'll switch to some values that are bigger than 3 that are getting, or -3 that are getting progressively closer and closer to -3. So like 2.9, 2.99, and 2.999. And then I'll ask my calculator to help me out and find the y values. So exiting back to the main screen, I typed my equation into y1, so I'm just going to ask the calculator to plug these values into y1 and look at what the number is. So to get that y1, I start by pressing the vars button. That's right below the down. I'm going to move over to the y vars tab. I'll select the function option, and there's y1 right there. So I'll do parenthesis -3.1. So that's telling me to do y1 of -3.1. So the calculator is going to plug the -3.1 in for the x's in the y1 spot. And I get that number. If I press second and enter, that'll recall the last thing I typed in, so I don't have to jump through all those menus again to get the y1. And I can just edit that to become -301. And I can, again, press second and enter and get it recalled again and do -3.001. So if I write down those, let's do that or something. So that's -836, -8336, and -83336. If I look at those, the y is getting smaller and smaller each time. It looks like it's growing without bound. That's telling me we're going to -infinity. Now I'm going to repeat that same process with the -2.9s. So I'm just going to go back, recall this, and change that to -2.9. And do the same thing again. I usually do 3 at a time before I write anything down because I can get all 3 numbers on the screen at once on my calculator. But that's all like up to. So I have 831, 8331, and then 83331. And again, those numbers are getting bigger and bigger without bounds. That tells me that we're going to +infinity. So the fact that we're going to infinities is confirming that, yes, I do have a vertical asymptote here. So do the same thing now for +3. I'm going to start the same way. I'll pick a number that's a little less than +3 and then get progressively closer and closer to +3. So I'll start with 2.9 and then do 299 and 2999. And then I'll go to something that's a little bit bigger than positive 3, maybe 3.1, and get progressively closer and closer to positive 3. So 301, 3001. And now it's punched this stuff into my calculator again. So I'll do it the same way. Just going to press second and enter, and we'll go back and update these. I think I'm going to start with 2999 because all I need to do is delete out the negative sign. So it's a little bit less button pushing for me. So then I'll go 299 because again, I just have to delete one number, and then 2.9, and I just have to delete one number. So that was a little bit less button pushing, is the only reason I did it in that order. Does it really matter what order I do it in? Of course it doesn't. You just have to make sure you're writing down the right numbers in the right spots, right? So again, my big takeaway is it looks like these numbers are getting smaller without bound, right? They just keep getting smaller and smaller, don't seem to be slowing down. In fact, they keep speeding up, right? Like each time it's like a magnitude of 10 difference. Now I'll change to 3.1. And again, doing the same thing, just using second and enter to recall the last thing I typed in, and then updating whatever it needs to be. So there's that. And again, we're seeing the same thing, getting bigger and bigger. Again, with each end going to a negative or positive infinity, that tells me that what we got is a vertical asymptote. And then my last one here for the horizontal asymptote, y equals 0. Remember, the horizontal asymptotes have to work a little bit differently than the verticals. Again, y is going to 0, but the x's aren't going to a certain value. So what I want is the x is just getting really, really small and then getting really, really big. This will be true for any horizontal asymptote. I could use the same x values anytime I want to do a horizontal asymptote. The vertical asymptote, the x value should be specific to where the asymptote is, because the vertical is at an x location. The horizontal asymptote's at a y location. So the x's really just are going to be kind of the same thing. I'm just going to start by picking progressively smaller and smaller numbers for x, and then progressively bigger and bigger numbers for x. So I usually do negative 10, negative 100, negative 1,000, positive 10, positive 100, positive 1,000. There's nothing magic about these numbers. You could have done negative 7, 256, 5,483. Like, you get kind of the same thing happening. But this is just way easier to type in my calculator. Yeah, Charlie?
Does it matter how many numbers there are?
Should probably do 3. 3 is usually enough. And I like having like a magnitude of 10 difference. So like something in the tens, something in the hundreds, something in the thousands. Is usually the way I like to do it. And it's like nice and systematic. That tends to never give you a big problem. All right, so let's go ahead and update this. So I'll go ahead and change this from 3.001 to negative 10. Delete out that other stuff I don't need. Press enter, and oh no, it gave me a fraction. Well, we talked about what to do here, right? If I recall this, and then I add on to the end that DEC option, the calculator automatically convert this to a decimal and give me that number instead of the fraction. To get that DEC, I press math, and then I'm going to choose this option 2. See, there's the DEC. DEC is short for decimal. So there's that one. And now I'll just recall and add this in. But I don't want to overwrite it because I don't want to have to go back through that menu and add the DEC again. So I'm going to do second and delete. Notice my cursor has changed from flashing black to flashing clear. Now when I type a number, it's going to add it in instead of like overwriting whatever was there. So I'll do that, and then I'll do it one more time. So there's those. I'll write those down. Negative 0.31 or 132, negative 0.010, and then negative 0.001. Again, I'm seeing here y going to 0. Each one is getting closer and closer to 0. Here, they're not growing very fast. In fact, they're kind of settling down to a specific number, right? So I'll do second and enter. And I think this time I'm going to start at the bottom, because if I do that, I can just delete one number. I don't have to insert. So it just saves me some button pushing. But it doesn't really matter the order in which I do it. So there's 1,000 plugged in. There's 100 plugged in. And there's 10 plugged in. Notice when I plugged in 1,000, it seems like I got something that didn't follow the pattern, right? So I have 0.0879, and then I have 0.0098, and then I have 9.98. That doesn't seem right. But look at the end of that number. You see that little e negative 4? What does that mean on our calculator when we see that? Times 10 to the negative 4. It's giving me an answer in scientific notation. So really what I need to do is I need to move this decimal place 4 to the left, and that'll really be the number. And now that looks right, right? If I go and I look at those, yep, heading to 0. That's what I was hoping for. So again, both heading to 0 confirms the horizontal asymptote at 0. So again, remember, that capital E is just how the calculator writes scientific notation, right? If I did 9.98 times 10 to the negative 4, it just gives me that same thing with the capital E in it. Those of you that done science class, if you did chemistry, you probably use that key a lot for Avogadro's number, right? 6.21 times 10 to the negative 20, or positive 23rd. Look at me, I still remember it. Grace, happy? Sure, of course, no problem. Anybody else? Great. Let's let the learning begin then. Today we're going to be starting section 1.7. We'll take more than one day to finish 1.7. This is a pretty beefy little section here. So section 1.7, we're going to start by talking about function operations. When we say operations in math class, typically you should be thinking of your 4 basic operations that you've been working with ever since you were just like a little squirt in elementary school. Those 4 operations being addition, subtraction, multiplication, and division. So let's start by defining what we mean for addition of 2 functions, subtraction of 2 functions, etc., etc. So our definition says, let f and g be 2 functions with intersecting domains. Then for all values of x in the domain, the algebraic operations performed on f and g are defined by the following rules. F plus g of x is just f of x plus g of x. F minus g of x is f of x minus g of x. F times g of x is f of x times g of x. And f divided by g of x is f of x divided by g of x, provided that the denominator is not 0. So what we're seeing here is just, if we want to combine 2 functions through one of our basic 4 operations, it works exactly like we would hope to, right? I can just take f and g separately and then add them together. I don't have to do anything weird with that. It's just the same thing as doing them one at a time, which is lovely, right? That's how we hope things to work, is just the same ways that it's kind of always worked. Just for the sake of example, let's run through and do a couple here. Make that a little smaller. There we go. So let's look at a couple of examples. So in this one, we're going to define the function f of x as 2x minus 3 and g of x as the square root of x plus 2. And then we're going to find the resulting function from performing the following operations. So our first example, we want to look at f plus g of x. Well, from my definition above, I know that that is the same thing as just taking f of x plus g of x. And the problem tells me that f of x is 2x minus 3, and g of x is the square root of x plus 2. So the only thing left to do now is to see if there's any simplification I can do. In this case, since it's an addition problem, I'm just looking to combine some like terms here. Do you guys see anything that I can do to simplify this? Kate, you're shaking your head no. Why not? Great. There are like terms of 2x and x, but the x is under the square root and the 2x is not. I know that we can't combine those two things unless they're both in the same location, either under the square root or out of the square root. Likewise with the negative 3 and the positive 2. So there's nothing more to do here. We are done. And it's like, boy, Mr. Kulik, that's like the dumbest thing I've ever seen. That was so easy. I kind of feel insulted that you even felt like you need to do an example of that. And it's like, simmer down, okay? We're just starting, you know, so we're not leaving anybody behind. So let's look at the next example. Here we're looking at f minus g of x. Again, using my definition from above, that's the same thing as f of x minus g of x. Oops, that wasn't the example, though. It was g minus f. Wah, wah. Let's fix that real quick. G minus f. Oops-a-daisy. You ever get going so fast you make a silly mistake like that? Happens to me all the time. It just, math is so exciting. All right, just like before, I'm going to replace the g of x with x plus 2, and I'll replace the f of x with 2x minus 3. How's that look to you guys? What do you think? Anybody got a problem? Oh, you should. This is wrong. Mr. Kulik's done something on purpose because it's a very easy mistake for you to make. Jake?
Does the f go before the g? The minus?
Nope.
Minus g?
That's not the problem. So here's the issue. It's tough to see. Here, if I look, the f of x is negative, right? So the entire f of x needs to be negative. So I need to make sure I'm distributing that negative sign through the entire f of x. I'm going to point this out now because if I don't show you this example, every single student typically does exactly what I just did and makes a mistake. I show you the example and point it out, probably still half of us are going to make the same mistake. So I'm going to sit here and talk and say it over and over again that when you're doing the subtraction, you have to make sure you're distributing through the entire function, hoping that of the half that would have made the mistake before, maybe half of you guys hear it and are going to avoid this mistake come the quiz or the test or whatever. But still, too many of us are going to make this mistake. So let me say it one more time, that when you're subtracting two functions, you have to make sure you distribute the subtraction through the entire function. Let's try to all catch that when the quiz or the test rolls around next. Because I promise you I'll do it to you again. I'm going to try to trick you again using the same tricks I show you. And you're like, Mr. Kulik, is it still a trick if you've shown it to me? Well, you can answer me after the test and see if you get caught by it. Because if I'm still catching most of you, it's still a pretty good trick. You guys all cool? You see how easy of a mistake that is to make, right? I wrote it in the naive way, and I got every single one of you to say, yep, that looks good. Bummer. All right, let's look at the next one. Here we have g times g of x. So again, according to our definition, that's going to just be g of x times g of x. So I know g of x, that was just the square root of x plus 2. So I'll just substitute that in. And then all I'm left with is to try to simplify this. How would I do that? Can I do that? Is there anything to do? I don't know. You tell me. I do know, but it's more fun if, for me anyways, if you guys participate. May not be any more fun for you, but what do you think? What can we do with that? Anything? Let me help you out. Yes, you can do something with this. What could we do? Let me give you a hint and ask an easier question then. If I just have a times a, what do we get? A squared. So if I have the square root of x plus 2 times the square root of x plus 2, what do we get? Excellent. Square root of x plus 2 squared. And what is that going to allow me to do if I think about it that way? Yeah, the square can cancel the square root, right? Boop! And we're out of there. I'm glad it's easy. That's what I'm hoping, right? It should be easy. If it's so easy, next time I ask, you just go ahead and shout it out when you see it, right?
Yeah.
Okay, no problem. And even if you're not sure, take a risk, right? Isn't that one of the MYP thingamajiggers, right? Or the IB thingamajig, be a risk taker or something? Sounds like one, doesn't it? And we mean an academic risk taker, not like, I'm going to try to jump my car over this lake. Don't try to do that. You're not going to make it. All right. Last example. Here we have f divided by g of x. Again, from our definition above, that's just f of x over g of x. I'll replace my f of x with the 2x minus 3, my g of x with the square root of x plus 2. That leaves me with this. Anything I can do with that simplification-wise? You might remember a rule from geometry about something that looks like this. Do you remember when you have a fraction with a square root in it? You don't want to leave the square root of the fraction in the denominator, right? That was kind of the rule from geometry. That was a long time ago. But when you're in geometry, did you ever see a problem where you had a variable under the square root? Or was it always just like a number? It's always just a number, right? Under the square root. So here's going to be what we're going to do in this class. If you have just a number under the square root, I expect you to rationalize the denominator, get the square root out of there. Jacob, by multiplying the top and bottom by that square root, usually does the trick, unless there's like +1 or something else attached to it. But typically that's all you need. If we have a variable expression under our square root, we're just going to leave it. I don't want you to do anything. So if I have an x under the radical, we're not going to ask you to rationalize any denominators. We're just going to leave it the way it is. Because, quite frankly, the simplification or rationalizing denominators kind of makes it grosser. We're just going to leave it. So if it's a number under there, just a number, yes, rationalize. If you have an x under there, I don't care what else is under there. If there's an x in there too, just leave it, man. Everybody cool? Great. So those are the four basic operations on functions. There is a fifth operation that we can do to a function. You would have talked about it last year in Algebra 2 classes. Anybody remember what that fifth operation on functions is? Starts with the letter C as a hint. Anybody remember? C is for composition. Okay. So we say if f and g are two functions where the domain of f intersects the range of y, the composition f of g, denoted as this set of symbols, is defined as f of g of x. Mr. Kulik, pet peeve time. You see that set of symbols that I've highlighted in pink? When you read that out loud, it breaks my heart when you say the word fog. All that does to Mr. Kulik is says, there's a kid that hasn't paid attention one lick in like the last 2 weeks. If you say fog, the little circle in the middle is not a letter O. That's the symbol for composition. That thing we've highlighted in pink should be read as F compose G. Okay? If you say fog, I just want to stab something. Sometimes it's me, because apparently I've been doing such a bad job. Sometimes it's you, because you're testing me and you're driving me nuts. But something is getting stabbed. All right? Ay, ay, ay. Okay. So let's look at what's actually happening here. When we do this composition, it looks like I'm plugging in the function g inside of f, right? That's what the definition looks like. It's just we're plugging f into g. Let's do some examples where we practice doing some compositions. When I say this, oh boy, that did not go where I thought it was going to. When I say this word, composition, does that ring a bell from last year now? Maybe, maybe not. Some of us had like 3 math teachers last year, so if some stuff got lost on the cutting room floor in the midst of 3 different math teachers in 1 year, I get it. But if you had all the same person the whole time, like, did Miss Nara have one of these all year long? Okay. All right. Well, let's do a couple of practices right now. Like, it's not difficult, but like if we're not familiar, if we haven't seen it in a while, or it was just kind of shakily done before, let's do a good job with it now. So we're going to do f compose g of x. From our definition above, I know that that is the same thing as f of g of x. And if I look at my example problem, I'm told that g of x is negative 3x plus 4. So I'm going to replace the g of x with negative 3x plus 4. Now, what does it mean when I write f of negative 3x plus 4? What should I do with that? What is that telling me to do? Okay, what if I just written f of negative 2? What would that tell me to do? Replace all the x's with negative 2's. Excellent. So what is f of negative 3x plus 4 telling me to do? Replace all of the x's with negative 3x plus 4. Oh, okay. Still kind of the same thing. So if I look at f, I have a 2. But where that x was, I'm going to write negative 3x plus 4. And then I have a minus 3, and where that x is, I'm going to write negative 3x plus 4. Right? So I took my G and plugged it into F. Does everybody kind of see what happened there? Okay, at this point the composition is done, but there's a lot of simplifying left that we could do here, right? And we should simplify this to get to a simplest form answer. What would be the first thing I'd want to do when simplifying this? So I see multiplication, I see addition, I see subtraction, I see exponents. What's the first thing I should do via the order of operations? The exponent, right? So how do I do negative 3x plus 4 squared? What's up? Sure, yeah, that's a good idea. So negative 3x plus 4 squared means negative 3x plus 4 times negative 3x plus 4. Everybody good there? So let's look at that first grouping. I have 2 times negative 3x plus 4 times negative 3x plus 4. Next thing we'd want to do is multiply in there. What should I be multiplying? There's 3 things being multiplied, right? Which 2 should I multiply together first? So Iden says distribute the 2. Does anybody say anything different? Turns out it doesn't matter. Okay? It doesn't matter. What I like to do is I would do the foiling first. Because what you don't want to do on accident is to do this, which is very tempting to do. I see students do all the time. That's incorrect. You can multiply that 2 into one location or the other, but you don't get to multiply it into both. Which is why I suggest foiling first, because then there's only one place to distribute the 2 through, and everything will be fine. So again, when we have 2 parentheses written next to each other, we multiply that using the FOIL acronym. So first, what is negative 3x times negative 3x? 9x squared. Good. Just shout them out when you know. And then outer, negative 3x times 4. Negative 12x. And then the inner, 4 times negative 3x. Negative 12x again. And then 4 times 4. 16. And then I'll recopy the rest of that. I notice inside that first parenthesis, negative 12x and negative 12x are like terms. They combine to give me, nope, negative 24x. Negative plus negative is also a negative, right? And then I'll distribute my 2 through. And I'll distribute my negative 3 through at this point. Worth stating, you could have distributed that negative 3 through at any point prior and it would have been fine. But you needed to be a little bit careful with that positive 2 there in the beginning. Out front? No, it's positive. That's okay. No problem. I miscopy things on occasion. If you ask a question about something, it just tells me that you're paying attention. That's perfectly fine. If you think there's a mistake and there turns out not to be one, that's okay. Please say something if you think there's a mistake. All it does isn't tell me you're paying attention, which is great. Okay? Even if there is no mistake and you're wrong, no big deal. I'm happy to take a look because it matters, right? All right. At this point, I can combine like terms, right? Negative 48x and positive 9x are like terms. Those combine to give me negative 39x. Positive 32 and negative 12 are like terms. Those combine to give me 20. And that can be my final answer. Notice here, this took a long time to get to, right? Will they all be this long? No, right? If you remember, we go way back here. The composition was done at this step. Everything after this was just simplification, right? The reason it took so long is because of the functions involved that we were composing. If they were different functions, it may have taken less time to simplify at the end, but the composition is easy. It's the simplification that can be some time-consuming, tedious. All right, let's look at the next one. Here we have G compose F of X. Oh, well, look right up here. We did F compose G, the previous one. Now we're doing G compose F. Won't that just be the same thing? Right? 2 plus 3 is the same as 3 plus 2. What if I do F compose G and G compose F? When I get the same thing? Well, let's find out, right? Let's do it. See if we do. So again, our definition tells us that's the same thing as G of F of X. And F of X is 2x squared minus 3x. And when I plug that into G, G is negative 3x, but in place of x, I'm going to put that other stuff, and then plus 4. So the stuff going in place for the x in G is that negative 2x squared minus 3x. And then I can just distribute the 3 through, since the exponents are just attached to the x. That's nice. And that's all the way fully simplified there. Well, that was a lot quicker, right? Well, what do you notice about these two answers? They were not the same. Oh no! What we've just seen, what we've just demonstrated, is the first time you've seen a mathematical operation that is not commutative. That's not the same answer forwards and backwards. Like 2 plus 3 and 3 plus 2. Not the same answer. Or this is not the same answer, right? Keep in mind. Now, does that mean you can never get the same answer? Of course not, right? Can anybody think of a situation in which you get the same answer, regardless of the order of doing the compositions? If they're both the same function, right? Clearly you'd get the same answer there if f and g were just the same function. Excellent. That's the easy, obvious situation, which we're going to kind of see in part C, right? So here is f compose f of x. So that's f of x. And remember, f is 2x squared minus 3x. So I just replace that. And now I'm going to plug 2x squared minus 3x into 2x squared minus 3x. So there's 2x squared minus 3x, but in place of x, I'm going to plug in 2x squared minus 3x. Oh, it's like functionception, functions inside of functions. That's like an Inception joke, which is a movie reference that maybe is not as relevant now as it was like 10 years ago, but somebody's probably seen it. Miriam shook her head. I'll take it. One person. Okay. So just like before, we have some simplification to do. For the sake of time, I'm going to do the foiling here quickly in my head. So that's going to be 4x to the 4th minus 12x to the 3rd plus 9x squared. And then we'll distribute that negative 3 through. It's minus 6x squared plus 9x. I'll distribute the 2, so I have 8x to the 4th minus 24x cubed plus 18x squared minus 6x squared plus 9x. So the 18x squared and the minus 6x squared are like terms. I combine those together for a final answer of 8x to the fourth minus 24x cubed plus 12x squared plus 9x. Woo! That jumped on me. 9x. Toot, toot, toot. And I'll pause here because I see lots of pencils moving. I did that kind of quick. This is the power you wield, though, as an experienced math teacher. Keep in mind that I am really no better at math than probably you are at the same age, but I've been doing this job for 16 years. Imagine how good at school you'd be if you took the same class over and over and over again for 16 years. You would look unbelievable at it, right? Everything would be fast. It would always be right. You wouldn't make mistakes. It would be pretty impressive. That's the only difference between what you're seeing when you watch me do these things and what's happening when you're doing these things. The difference is thousands of hours of practice. That's it. You could be a math teacher too. All right. As a quick aside, notice how quickly I did this. Mr. Coolidge did not actually foil when he did this. He remembered this perfect squares factoring pattern from Algebra 2. You would have seen this last year. So he thought of this guy as A and this guy as B. So A squared, 2x squared squared, 2 squared plus x squared squared is 4x squared. And then this is 2 times A times B, so 2 times 2x squared times negative 3x. That's my negative 12x cubed. And then the 9x squared was B squared, so that was negative 3x squared. Negative 3x squared is negative 3 squared 9, x squared squared. So 9x squared. In case you're wondering, Mr. Coolidge, you seem to foil that so quickly and effortlessly. How did you do that so quickly? That's how he did it so quickly. Not that you needed to remember that. You can certainly have foiled in that situation. It's no reason not to, other than you save yourself a little bit of time and effort if you remember that formula and use it appropriately. But you don't need to. Now, function composition is actually a very, very important operation. And little did you know, you've been using it all the time, even prior to learning that there's such a thing as function composition. So we'll explain here in the next, probably not get to it quite today, but soon we'll kind of show you why you've been doing this the whole time and you didn't realize it. The beginning of that explanation is that we use function composition to define the concept of an inverse. So let's look at what that means. Again, this is a term that you should remember from Algebra 2 last year, assuming that you had a good Algebra 2 experience, which I know was not the case for all of us all the time. So this definition says, let f and g be two functions. We say that the function g is the inverse function of f, provided f compose g is equal to g compose f, and both of those simplify down to x. In this case, the function g of x, we would write with the symbol f with the little -1 superscript of x. We read this, though, all as one thing. We read that as f inverse. That does not mean f to the -1. Again, that hurts my ears. That's all one name. That's read as f inverse. It does not mean f to the negative 1 power. If you remember what the negative 1 exponent means, it does not mean that here. It just means the inverse of f. So what we're going to do here for the rest of today is we're going to talk about how we find inverses of something. Before I do that, though, let's give a little bit of example of kind of what this idea of an inverse is saying, right? So let's say that f of 2 is equal to 6, right? What f inverse needs to do is it needs to take the output of f and return back the input. What f inverse is doing is it's basically undoing whatever f did. If f is the map from 2 to 6, then f inverse has to take 6 back to 2. It's basically the way home, right? It's the return leg of your journey. Everybody's okay with that idea? Okay. So what we're going to talk about next is going to be about finding inverses. And we're going to look at a couple of different situations because, again, back in like section 1, we talked about like there being 4 different representations we use for a function. We're going to look at each of those 4 representations and how to find the inverse in those situations. So the first situation we're going to look at is if we have a mapping diagram. So let's look at that example. All right. So let the function f of x be the indicated mapping diagram below. Find the inverse function g. So first thing, let's look at f real quick. Is f a function? It says so in the problem, but how do we know? Every x gets used, and each x goes only to one place, right? That's the 2 things we need. F is definitely a function. So what does f inverse have to do? Well, I know when I set it up, it needs a domain and range. What numbers are going to be in the domain for f inverse?
4, 5, 6.
Excellent. 4, 5, and 6. Those are the outputs or the range values for f. And what are going to be the range values then for f inverse? 1, 2, 3. The domain values for f. So far, so good. Okay. Where does 4 need to go? Back to 1. Where does 5 need to go? Back to 3. Where does 6 need to go? Back to 2. And this is my f inverse. I'm done. Yay! That was so hard, Mr. Kulik. I basically just turned the thing around and it's done. Yup, it's that easy. Quick question before we move on to the next thing. Is f inverse a function?
Yes.
Yes. All the x's are used, and they're each used one time, right? Okay. Let's look at the next situation. What if we are looking at a set of ordered pairs as our function? Right? That was the next representation we looked at. So let f of x be given by the following ordered pairs: -2, 4, -1, 6, 3, 8, and 5, 8, what would F inverse be in this situation? Well, think about it this way. This is like F sends -2 to 4, and sends -1 to 6, 3 to 8, and then 5 to 8, right? What should F inverse do then? If we're going from -2 to 4 for X, or for F, F inverse should send 4 back to -2. What should the next one be? Somebody take a risk.
6.
Yeah, just shout them out. It's okay. If I'm just like, just yell them out if you know. Impress me. And everybody else, What's the next one? 8, 3. Awesome. So quick. The next one? 8, 5. Very good. Thank you. I love the participation. Okay. Everybody see what we did there? What did we, in your own words, what did we do? Switch the X and Y. That's all we had to do. Done. Easy, right? Okay. Is F inverse a function? No. Why not? Yeah, we have a repeating X coordinate, right? That X coordinate went to 2 different locations. F inverse is not a function. Oh no. Let's look at, we had one situation where F inverse was a function and one where it wasn't. I wonder if there would be a way to predict, just by looking at F, whether the inverse was going to be a function or not. What do you think? Of course there's a way to do this. Why would I lead us down this path if there wasn't? That would be really kind of like false advertising, Mr. Kulik. You wouldn't do that, would you? Probably not. So to do that, I have to define a few terms. So I'm going to put up 3 new terms here real quick, and then we'll talk about what these things mean. And we'll go back and do some examples and show you like what I'm looking at to tell. So those 3 terms are the terms onto or surjective, one-to-one or injective, and both at the same time, which we say is called bijective. So we say a function is considered onto if every element in the range is mapped to by some element from the domain. This just means that all the ranges are used. That's all we're saying. All the ranges have to be used. Okay. Fine. That's easy enough. One-to-one. A function is considered one-to-one if every element in the domain maps uniquely to distinct elements in the range. What's that mean? The ranges only get to be used one time. Okay? Fine. And then something that's both one-to-one and onto is called bijective. What does that mean? Any element in the domain or range, they're all used, and they're all used once. So if you have a function, all the x's are used and they're only used one time. If it's one-to-one and onto, the ranges all are used and used just one time. I'm going to pause here because I still see lots of pencils going, but we're going to scroll back to those previous 2 examples and look at those and try to decide if those are one-to-one or onto. Everybody okay with that? That's what we're heading to next. All right. I'm going to scroll back. So let's look at the F here in example 13. Is this onto? Are all the y's used? All the things in the range get used? Yes. So is it onto? Yes. Right? Everything got used. Is it one-to-one? Yes. Each of the ranges are used one time. Right? So what can we say then? It's bijective. So we've seen that a bijective function has an inverse that's also a function. Right? Let's look at the next example and see if that one is bijective also. So here, F is the set of ordered pairs, -2, 4, -1, 6, 3, 8, and 5, 8. Is this onto? What's the range of F? 4, 6, and 8, right? Are all those used? Yup. Is it onto? Yup. Okay. Is F one-to-one? No. Why not? Yeah, the 8s are used more than once. Notice here, it wasn't bijective. We had only onto, and F is not a function. So it's certainly, or F inverse is not a function, excuse me. It's a big omission of a word. So it appears that at least one-to-one is a necessary condition for the inverse to be a function, right? We see that if we don't have it, we might not get it. The next question is, do I have to have onto also? Let's look at an example of a function that is one-to-one but not onto, and look at its inverse. Okay? What we want to do is check to see if we need both of those two things. Because we've seen if we have both of them, we're going to get a function. But maybe we just need the one-to-one. Maybe we don't need onto. Right? So let's look at this. So domain, range, bloop, bloop. Is that a function? All the x's are used. They go to just one place. That works. Is this onto? No, right? One of the ranges is used. Is not used, right? Not onto. Is it one-to-one? Well, yeah. Right? It's one-to-one. If we make F inverse here, we'd have this. Is this a function? What do you say? No! Excellent. Why not, Lexi? Absolutely. Not all the domains are used. So it appears that if I don't have onto, I might not get a function. If I don't have one-to-one, I might not get a function. I have to have both one-to-one and onto to guarantee that F inverse will be a function. Everybody convinced? Well, that's lovely, Mr. Kulik. So let's kind of keep on going and keep on exploring what's going on here. So we've only looked at two of the different ways of representing a function, finding an inverse from that. Let's look at how we do this if we have a graph. because those previous two representations of functions, like we just don't use those very often. So like even though I can tell one-to-one and onto from that, it's I don't use those very often. It's really just not that helpful to me, Mr. Kulik. Let's start looking at the good stuff, the stuff that I use, like graphs and equations, right? So here's a graph. This graph represents some function f of x. How do I how do I draw the graph of f inverse? Jake? Flip it how? Nope. Which side? Better way of thinking about it. Anybody else with an idea? Notice you're given 3 points here on the function. What can I do with those 3 points in the what would those 3 points become in the inverse? Kate? You'd flip the x and y coordinates, right? So instead of having 0, -3, we'd have -3, 0. Instead of 1, -1, we'd have -1, 1. Instead of having -2, 5, we'd have 5, -2. 1, 2, 3, 4, 5. 1, 2. Everybody's okay there? But how am I going to connect these now? Well, here's my advice. The vertex in F will still be a vertex in F inverse. Okay, and the shape is basically going to be the same. So I can just kind of like do one of those. That seem easier than what you're describing? To just transpose the coordinates and draw the picture that way? Probably easier, right? Now, you're not wrong in saying that there's a way to do this by just reflecting. If you remember back to your Algebra 2 class, you might have also talked about the graph of an inverse is a reflection across the line y equals x. So if I draw that line y equals x, that's the line, y equals x. So if I look, like this part of f becomes like this part of f inverse. So it's kind of like folding across that diagonal. Now, I think that's really hard to visualize and to do. I find it much easier to transpose the points, but I like drawing that line in afterwards as like a check. Because when I draw the line in and I look, I'm like, okay, that looks like a reflection across that line. To actually just take it and do the reflection myself, I think is kind of hard. But drawing it in afterwards, I'm like, that looks good. That makes sense to me. I like doing that. Does that feel okay, guys? Do you remember that? That the inverse is a reflection across the line, y equals x. Some of us may, some of us might not. Either one is okay. So as an aside, if I look at f inverse, is that a function? F inverse is our graph in red. Is that a function? No, why not? Excellent, yes, okay. So here's the big question then. What was f not 1-to-1? Was it not onto? Was it neither? Which one did it fail? Because the inverse wasn't a function, so I know it was missing either 1-to-1 or onto, or it is missing both. How can I tell? Just by looking at the graph. Remember what onto meant? That the y's could only be used once, right? So if I look at this point, that's 2, -5. and I look at this point, that's the point 2, 5, I notice that, hey, there's a y that's used more than once. Everybody agree with that? What do I know about points that have the same y? Well, those points lie on the same horizontal line, right? So I can check if the graph of a function is 1-to-1 by doing a horizontal line test. Everybody's okay with that idea? Let's write down what we mean there. Okay, let's put some words, attach some words to that. So we say the horizontal line test defines y as a 1-to-1 function of x if and only if there is no horizontal line that intersects the graph at more than one point. So the HLT, the horizontal line test, will tell us if f is 1-to-1. If f is 1-to-1, it'll tell us that f inverse is a function. Because here's the little secret, guys. When we draw a graph of a function, they're all onto. If we write the equation for a function, they're all onto. The only thing that we're going to ever miss is the 1-to-1 piece. Just by the nature of how we kind of do things in our algebra class. I'm not going to get into the nitty-gritty of why they're all going to be onto. You're just going to have to take my word for it because it's like a longer discussion than I really feel like is relevant to the class. It doesn't really add anything, and it's just kind of complicated and very detailed in a way that's like not going to be more informative for you. So I'm just going to ask you to take my word for that. But this is lovely, right? Because graphs are pretty easy to generate. Even if I have an equation, I can usually get the graph out of it. And a horizontal line test, I love that's just as easy as a vertical line test, which we all did so well with. Last time I gave you a quiz and I asked you if something was a function or not, everybody seemed like they just used the vertical line test and did so correctly. It was great. This is the same idea. It's just going the other way. And instead of telling us whether f is a function or not, it'll tell us if f inverse is a function or not. Cool? Okay. All right. Next and last situation is if we're given an equation. And we're going to do this one example here, and then we're going to stop here. We have a whole heap of examples after this to get through. Because quite frankly, although the process is the same every time, like the algebra steps are different and they can be a little bit complicated, but they also provide me a good opportunity to review things from last year. So we're going to do a whole heap of examples of this type, but we're just going to do one to start here today. So here, we're given an equation to represent our function. Here are the steps that we use to turn an equation into an inverse, or f into its inverse, where f is represented as an equation. These are going to be the same steps every time, but depending on what f looks like, the algebra I need to use to accomplish these same steps can be very different, okay? My first step is going to be rewrite my equation with a y instead of an f of x. Well, that's pretty easy, Mr. Kulik. The next step is going to be get the x by itself. This is the one where the algebra can be very different depending on what your function looks like. In this case, to get the x by itself, I need to first, what? Ooh, I would not do that first. You'd have to be very careful if you're going to do that first. Instead, I would rather add the 7. Now, I want to be clear, Maura, that dividing by 3 is not necessarily wrong, but you have to be really careful when you're doing it. Typically, when we're solving, we go the reverse order of operations. We want to start by undoing addition, subtraction, and then multiplication, division, and then exponents, and then inside the parentheses, as opposed to simplifying, where we go this way. So that's the way I like to remember it. It's a reverse order of operations. Okay, so we did that. And then now let's divide by 3. It's okay. I love that you went for it and took a risk. Even after you said it, you're like, oh, I don't want to say this, and you still did it. That's great. Please tell me what you're thinking. 1, it tells me where you're at. 2, it gets you immediate feedback, right? And it's that much easier to like make a correction in the moment before we even get into the homework and go, oh yeah, I would have probably done that for all these problems in the homework and potentially made a bunch of mistakes that I get clarification on right now before we've even started. Okay? So even if you say things that are wrong, I'm glad to hear them. And in your case, it wasn't even necessarily wrong. I want to be clear. It wasn't wrong. You just have to be careful. I'll do an aside here in a second to show you like what I mean by being careful. Okay, we're almost done. The x is by itself. The next step is I'm going to change the names of my variables. I'm going to rewrite y as x, and I'm going to rewrite x as y. What am I essentially doing? Remember when we did the set of ordered pairs, what were we doing? Switch the x's and y's. That's what I'm doing here. That's the same thing. This is the algebraic equivalent of just switching the x and y coordinates. At this point, I'm done. I'm just going to rewrite the y as f inverse. And that is my answer. Everybody okay there? Great. Maura, I want to show you why you're not necessarily wrong, but why we have to be careful. If you divide by both sides by 3, if you do it like this, you're going to be wrong. If you do it like this, and everything gets divided by 3, that will be fine. In my experience, most students don't remember to give everything divided by 3. Yeah. And then we can subtract the 7/3. And you're at the same place you were before.
I'll just do it the other way. It's okay.
That's my recommendation also. But I want it to be clear that you're not wrong. Okay?
Thank you.
Yes. Okay, couple of things before we finish. The assignment for not this Sunday, but next Sunday is going to be 25 to 56. That's a lot of problems. I understand. Take a deep breath. At this point, I think you guys can do up to like 53 or 43. Okay? What's due this Sunday is 19 to 24, right? Plus the delta math, right? Remember, the delta math, the way it's set up, you're not penalized for wrong answers. You do not need to get 4 correct in a row, or all of them correct in a row. You don't need a streak. Of each problem type, you just need to do 4 correct eventually. 4 correct of each problem type. There's 6 types. But look. Some of the types are multiple choice, don't require much of anything. Some of them are just like, is this a function or not? like what's, convert this to an interval, this inequality to an interval. Like they're not super complicated. They shouldn't be terribly time consuming. There's one particular question looking at the domains and ranges for like real life situations that like there's a lot of parts to, but the other 5 types of questions should be pretty quick and easy. Okay? So that's what's going on here. Next week we're going to finish up 1.7. We'll take a data review, and the following week is probably looking at the date for chapter 1 test. So just FYI, that's coming up in the not too distant future, chapter 1 test, the week after next. Okay. Any questions for me? Okie doke.
You'll know that.